Okay, so good afternoon, everybody. I'm Valeria Grisoni, and I am an astrophysics fellow at the National Institute for Astrophysics in Italy, in particular here in Trieste, at the Observatory of Trieste. And today I will talk about near-field cosmology, and in particular about the formation and chemical evolution of the Milky Way, our own galaxy, which is a benchmark to understand galaxy formation and evolution in general. So a brief introduction. My field of research is basically called galactic archaeology, and we aim to unveil the history of formation and evolution of galaxies as our own galaxy from chemical abundances and stellar ages that are fundamental constraints to reconstruct the galactic history. And tomorrow there will be the talk by Francesca Matteucci, which that I'm sure will give a great overview about this field of research, going also beyond the Milky Way. And so not only local, but now I will focus on the Milky Way, so our galaxy, and in particular my expertise is in the development of chemical evolution models, thanks to which it's possible to predict the chemical abundances expected in each galactic component, and we can then constrain the history of the galaxy. We know that the galaxy has four main stellar populations that differ on the basis of chemical and kinematical criteria. We have halo stars with eccentric orbits and low metallicities, thick disk stars with properties in between the halo and the thin disk. The thin disk stars having almost circular orbits and on average a solar metallicity, and then the bulge stars in the center of the galaxies having random orbits and a wide range of metallicities. In my study, I've mostly focused on trying to understand the dichotomy in the disk, so the bimodality between the thick and thin disks that we see in chemistry. Okay, so the data from which I've started have been mostly Ambre data that show that in the abundance factors of alpha elements such as magnesium, we see two distinct sequences corresponding to the thick and thin disk stars, with the thick disk stars being alpha enhanced with respect to the thin disks. So they have higher alpha values and lower metallicity with respect to the thin disks that represent a low alpha sequence tending to higher metallicities. And color coding differently, there are these metal-rich alpha enhanced stars in blue that still needs to be well understood by chemical evolution models. So the models that I developed for the thick and thin disks follow basically two main chemical evolution approaches. A revised two-infall approach that I applied only to the disk, so not taking into account the halo. In this scenario, we assume that the galactic disks formed by means of two infall episodes. The first one giving rise to the thick disk, and a second one giving rise to the thin disk, delay with respect to the first one, and on a longer time scale of formation. And then also a parallel approach where the two disks start forming at the same time, but they evolve at different rates. So also in this case, with the thick disk forming much faster than the thin disks that evolves much more slowly. And this is what we have in the alpha over iron versus phi over h diagrams for the two scenarios, the two infall and the parallel. So in the two infall, we have a first phase corresponding to the thick disk formation that match the thick disk data. Then we have a gap due to the assumed threshold in the star formation process, and then the thin disk forms on a thanks to a second infall event and evolves much more slowly, matching the thin disk data. On the other hand, in the parallel approach, we disentangle the evolution of the thick and thin disks, but also in this case, we have a thick disk forming much faster, and so it's alpha enhanced with respect to the thin disk that evolves slowly. And in this scenario, we can simply explain the metal-rich alpha enhanced stars as metal-rich thick disk stars at variance with the two-infall model, where the only way to explain them was by assuming radial migration from the inner regions of the galaxy. Then going less local from the solar vicinity to other parts of the galaxy, it's important to study abundance gradients that we observe in different chemical elements. And the fundamental question in this case is, how do gradients form? We have to mention the inside-out scenario, namely that the inner parts of the galaxy form much faster than the outer one. And then there are other ingredients that we need to include in our model to explain abundance gradients, namely a variable star formation efficiency, higher in the inner parts than in the outer one, or radial gas flows flowing along the disk. And here I show the abundance gradients of magnesium observed and predicted, where the observations are coming from Seyffarth and Young and clusters that can trace the present day gradient, and they are compared with observations from my thin disk model, including inside out scenario and other ingredients. And we say that, okay, so the inside out is important, but we need to include also other ingredients in our model, such as a variable star formation efficiency and the radial gas flows. And after the alpha elements that have been very useful to separate and understand the dichotomy between the thick and thin disk, we decided then to apply our models to follow the evolution of also other chemical elements, from the light one up to the heaviest one, from lithium up to the europium. And the lithium represents another lively topic in galactic archaeology, the understanding of the galactic lithium evolution that mainly relies on the understanding of the lithium plot. So the plot consists of the lithium abundance as a function of metallicities, and the important features that we see in such a plot are the so-called speed plateau at the low metallicity, and then we have the steep rise at the higher metallicities. And in this case, we can have to say that lithium is produced in the Big Bang, but also by stars of different kinds, as well as by cosmic rays. And in particular, we have the steep rise that is mainly due to novae. And in this case, our model have to reproduce the upper envelope of the data, since lithium is very easily to destroy. So with our model, we aim to reproduce the upper envelopes. And I apply my models to understand the dichotomy between thick and thin disks in lithium. And indeed, we can see a dichotomy also here, so a bimodality, with, in this case, the thin disk being lithium enhanced with respect to the thick disk that evolves faster and as its track shifted to higher metallicities. And the thin disk is lithium enhanced due to novae that have more time to contribute. Then I would like to talk about also the heavy elements, and so neutron capture elements that are elements beyond the iron peak that are mainly formed through neutron capture on heavy seed nuclei. And in this case, there are two possible cases. So the S process, slow with respect to the typical timescale of the beta decay, or rapid R process relatively to the timescale of the beta decay. In the case of the S process, we have that the main production size are mainly low mass AGB stars between 1.5 and 3 solar masses. Massive stars can also produce some neutron capture via the S process, but in this case, the neutron flux is quite weaker. And then in the case of the R process, an extremely neutron-rich environment is required. And in literature, several productions have been proposed, such as core collapse supernovae, electron capture supernovae, magneto-rotationally driven supernovae, and finally neutron star mergers. And here I show the result for europium. And in the case of europium, which is a typical R process element, we have something quite similar to the alpha elements. And so the three sequences corresponding to thick disk, thin disk, and also in this case, I plotted the bulge, for which we assume an even faster formation, shorter timescale than the disk. And this is similar to the alpha, since also in this case, we have a short timescale of production for the main production of europium, which are neutron star mergers. On the other hand, in the case of the S process, such as zirconium, lanthanum, and cerium, the situation is much more complicated, since they have different production sites, particularly low mass AGB stars that have timescale occurring on longer timescales. And after chemical abundances, as I said, another fundamental constraint for galactic archaeology is represented by stellar ages that are now representing a fundamental constraint for our models. And there are different methods that have been developed for the age dating, consisting in isochrone fitting, gyrochronology, chemical clocks, and particularly astrocosmology has been found to be really useful to give ages for galactic archaeology purposes. What is astroseismology? Well, through astroseismology, we are able to detect the solar-like pulsation in thousands of giants. using data collected by asteroseismic missions such as Corot, Kepler, K2, and TESS, and the pulsation frequency are then directly linked to the stellar structure and to provide the tight constraint on stellar properties and evolutionary state. And in particular, so we can get very precise ages that can be used for galactic archaeology results. And for example, some of the first results using Cosmology survey, I found that the most metal-rich stars are not the youngest. So this is a clue for radial migration effects. Or like the thick disk is a genuine old thick disk forming on a short time scale, and so confirming like the parallel scenario model. And or they provided also the time evolution of the metallicity gradient. So not only in the present day gradient that we use to constrain our model, but also how it goes back with time. And now we have new samples with very precise asteroseismic ages coming from asteroseismic missions such as Kepler, TESS, and K2 that can be coupled with spectroscopic surveys such as Apogee and Galan. And we found new results for the metallicity gradient, finding that it flattens going back in time. And we have now very precise ages that have confirmed the results of Cosmology with this new K2 data, and can also further constrain the model ingredients that I presented before. And also we can have precise chemical clocks, and chemical clocks consist mainly of an S process element versus an alpha element with very different time scale of formation, and so they have certain slopes, and we found that these slopes changes with radius, and we compared with our models for the thin disks. And for example, here I show model A with an higher star formation efficiency that reaches very high serum over oxygen values with respect to the model C that evolves much more slowly and resembles more the outer parts of the galaxy. So also in this case, we are finding evidence of radial migration. So yeah, here I conclude with a summary. So chemical abundances can tell us a lot about the nucleosynthesis as well as the formation and evolution of galaxies, such as our own Milky Way galaxy. Chemical evolution models can then follow the evolution of the different galactic components. And in particular, I presented results for disks, the thick and thin disks, where we have a clear dichotomy in the alpha over iron versus phi over H plot. But we can see this dichotomy and this bimodalities also in other abundance patterns, such as the plot of lithium and europium, whereas in the case of the S process, the situation is different due to the different production sites for the S process elements. And in particular, I concluded about talking about the importance of the synergy with asteroseismic missions that also can allow us to have very precise stellar ages and to use them to further constrain our chemical evolution models and our understanding of the formation and chemical evolution of the Milky Way. And I conclude here, and thank you for your attention.